Okay, so last week we started the new section dedicated to proof Wang's conjecture in the odd case, and we will provide an example saying that the conjecture is not true for the even case. So to reconsider. So we are in a pivotal fusion category. You take a simple object Y, which is self-dual, and such that, so in this case, the Hom space between 1 and Y tensor Y is one-dimensional, because, as I said, this is there is an I-junction isomorphism into Y star Y, but Y star is equal to Y. So it's a Hom space between the Y and Y. Y is simple. So it's one-dimensional by Schur lemma, because we are in a field which is algebraically closed. Remember that the Schur lemma is saying that the Hom space between a simple object and itself is a division algebra. So for that to be one-dimensional in the finite-dimensional case, we need the field to be algebraically closed. Okay, so this is one-dimensional. And so by some previous proposition about the reformulation indicator, this is second root of unit, 1 or minus 1. And the Wang's, so this theorem is saying that if this Hom space is one hot dimensional, so if there is a component, there is a Y component here with multiplicity odd, again, Y is self-dual, simple, and X is general, then in this case, this forces the reformulation indicator to be 1. Here we said it can be 1 or minus 1, but this forces it to be 1. Okay. So that's very useful, in fact. Okay. And we will see an example when this is even dimensional and this is minus 1. So this cannot be extended in general. Okay, so let me write that. So this theorem states the odd case of a conjecture due to Zhengwei-Wang. The odd case of a conjecture by Zhengwei-Wang. So he stated this conjecture here in 2010. At least I found a paper at this year. I don't know if it was stated before. So the even case is false if you consider this category of representation of a finite group with the group to be of Lie type PSU32. This is a counterexample. So this is a counterexample. So you have here, you can find, in fact, you can find two simple objects, X and Y, such that this is even dimensional, but this is minus 1. Okay. And in fact, this example is the smallest possible example coming from a finite group of the form ref G. Like the smallest one from finite group. Theory. Here the order of the group is 72. And let me mention that this example was found independently by Yilong Wang, independently by Yilong Wang in some unpublished note. Okay, so the goal of this section is to prove this theorem. So if we will need to prove, in fact, one proposition before, one corollary, and then we can prove the theorem. So proposition. So I am still following the numbering of my paper. Question 4.1. Okay, so this proposition, so you see the statement, the theorem is pivotal fusion category. But we can prove something, some preparation proposition for general pivotal monoidal category. So step by step, we will be closer and closer to this result. But we can state something at the level of monoidal category. So let's see, be a K-linear pivotal monoidal category. Let A be the pivotal structure. Okay. So let Y be an object not necessarily simple a priori here in C such that the home space of Y tensor Y1 is one-dimensional. Then we will consider a morphism, a non-zero morphism between Y and Y star. For any non-zero morphism kappa between Y and Y star, and we will consider also another object. And for any object X in C, we will consider the following bilinear form from the home space between 1 and X tensor Y tensor X star square to end of 1. So here we don't need to specify that end of 1 is equal to the field itself. We don't need to assume that. Consider the following bilinear form from bilinear map from, so as I said, so home from home C1 x tensor y tensor x star square to and C1. Let me just write something. Okay, so okay, like that. So I will draw a picture for this bilinear map. So you need to take two elements, two morphism here, and then you get here. So this bilinear map omega, omega alpha beta as follow. So you have alpha and beta in the same home space. So x, y, x star, x, y, x star, x, y, x star, x, y, x star. And so, and then here, so we need to use kappa, and we will use also the pivotal structure. So here, you need nothing. You can just put this evaluation map. For the y, we will use the kappa between y and y star. So then we'll get a y star here, and then we can make evaluation map. So let me add the kappa here. Then evaluation map. And for here, we will need just the pivotal structure. Then we have x double star, and then you can have the evaluation map for x star. Okay. So this is exactly the bilinear map we want to consider, and the proposition state that you can switch the order up to multiplying by a second Frobenius indicator of y star. So that's very useful. Okay. So proof. So we will use what we called lemma 2.4. So what was this lemma 2.4? Yeah. So remember, we prove a lemma 2.4 in which we already switch alpha and beta in some other context, up to considering some pivotal structure. So let me write. So by lemma 2.4. So we can apply some lemma 2.4 here for this and this, I guess, and we can switch this one up to adding some pivotal structure. So this is lemma 2.4, and we will also use the pivotal structure AX tensor Y tensor X star equal AX. So this is the usual definition of pivotal structure. So what can we draw? What can we draw just by that? So omega of alpha beta is, so as I said, you can move by lemma 2.4. You consider this as a big morphism, this as a morphism, and by this lemma, you can just move, you can switch these two, and you need to add this pivotal structure. But this pivotal structure is equal to that. So we can directly write the following. Beta alpha. So you have the pivotal structure decomposed. AX, AY, AX star. And you have the big block. You can just rewrite it. AX kappa and identity. And so we just have that. Okay, so this is just lemma 2.4 and pivotal structure. There is nothing else. Now we want to what do we want? We want to recover this shape here. So in particular, we want to delete some pivotal structure. There is too much pivotal structure here. Okay. So let me. So here we apply a previous lemma. Remember, this lemma was about computing the dual of evaluation map and co-evaluation map. The dual of evaluation map of X is the co-evaluation map of X star, and the dual of the co-evaluation map of X is evaluation map of X star. So the double dual of evaluation map of X is evaluation map of X star star. So we need to use that. And by pivotal structure, the other by pivotal structure applied on Fx. So you take the double dual. We have the double dual here. So remember, we have a formula for the double dual in the definition of pivotal structure. We have Fx double dual composed with this pivotal structure is nothing but Fx. Remember here, we don't write the object equal to 1. So if you put the other way, Fx double star. So we replace this by this, and we move. We move nothing. So it's just like that. Ax tensor Ax equal evaluation of X. Okay. So we have had that. So that may correspond to something here. So you have this one. So I guess this one can be deleted because you see, this is evaluation map of X double star. This is this. So you can replace everything here by just like that, which is that. So that's a good first step, but it's not enough. We need more. So move by lemma 216. So this lemma, in fact, let me 216. Yeah. So this lemma, in fact, was involved some kappa morphism as we have here, which is moved from right to left up to multiplying by the second formation indicator. So this is exactly what we will apply here. So we stated this lemma by a picture and by a formula. So let me write the formula, the exact formula we will need to apply here. Evaluation map of y star composed with AY tensor kappa equal second formation indicator of y star evaluation map of y composed with kappa tensor identity. So what this is just saying? This is just saying that you can replace this part just by putting the kappa here, so nothing here, and kappa here. This is exactly what this formula is saying. There is nothing else. So you can move the kappa from right to left. You here identity, here just kappa, and the Piotr structure disappear. So we already do that. So now we have that with kappa. So this is exactly the shape we wanted to recover. And as I said, you move kappa from here to here by up to multiplying by a constant. Second formation indicator. So the results follow. By combining these two applications of lemma 2.2 and 2.16, it follows that omega alpha beta is second formation indicator of y star beta alpha So now this is clear. Kappa, as I said, and here you have AX. As I said, this is nothing but second formation indicator of y star times omega beta alpha. Okay. So that's not very nice. Okay, so we are done. We are done for this proposition. So you see how the preliminary section was important here, because in fact, up to the lemma proved in the preliminary section, the proof of this proposition is almost immediate itself. So that's why it's very important. Okay. Now, corollary. Corollary. So what about this corollary? So in this corollary, it is still in the for monoidal category in general. So, okay. So this corollary can be seen as a generalization of the theorem we want to prove. In fact, in this corollary, we need to assume some bilinear form to be non-degenerate. Then in the theorem, the big part of one part of the theorem will be to show that in the fusion category case, the bilinear form we consider is really non-degenerate. And for that, we will also use what we did in the preliminary section. So let me state this general corollary. Let's see, be a K-linear pivotal monoidal category. Linear pivotal monoidal category with and C1 isomorphic to the field. So we need this assumption. Consider two objects, X and Y, such that the Hom space between Y tensor Y21 is one-dimensional, and the bilinear form as defined in previous proposition is non-degenerate. Then we will be able to state something as for the theorem 1-1. If the Hom space between 1 and X tensor Y tensor X star is odd dimensional, then the second Frobenius indicator of Y star is equal to 1. So let X, Y be object in the category C, such that the Hom space Y tensor Y1 is one-dimensional. And the bilinear form omega in previous proposition is non-degenerate. Okay. If the Hom space between 1 for X tensor Y tensor X star is odd dimensional, then second Frobenius indicator of Y star equal 1. Okay. Okay. So proof. So here, in fact, so this corollary don't assume the field to be of characteristic 0. In fact, here the field can be of any characteristic. Maybe we need the field to be algebraically closed. We should need that, but we did not assume the characteristic. And in fact, if the characteristic is 2, then it's immediate. So by the proposition 215 stating that remember, you have something like that. Here is 2. So it can be plus or minus 1, but in characteristic 2, minus 1 equal plus 1. Because minus 1 equal 1 modulo 2. So that's obvious in this case. So we can assume that the field is not of characteristic 2. Okay. So we will assume the second Frobenius indicator of y star to be minus 1, and we will reach the contradiction. So if make this, so we make this assumption, then by the previous proposition, the bilinear form, omega is represented by a skew. So satisfy so let me write that. Satisfy something like that. Alpha beta. Remember, we have just this is up to this constant. So we assume, if you assume this constant to be minus 1, then we have that. So you can directly say that this bilinear form is represented by a skew-symmetric matrix. So every bilinear form can be represented as a matrix. And the fact that when you swift the entry, you get minus 1, it means that the matrix is skew-symmetric, and skew-symmetric is just, the transpose is just minus, like that. So linear form is represented by a skew-symmetric matrix. Skew-symmetric matrix M. So skew-symmetric. Which color? This one. Transpose of M is minus M. Okay. So, but the determinant of the transpose of a matrix is equal to the determinant of the matrix. And the determinant of minus a matrix is minus 1 power n, determinant of the matrix, with n, the dimension of the space. So you see here why we consider the dimension of the space, where n is the dimension of the home space. 1 x tensor y tensor x star, which is odd by assumption. Okay. Odd by assumption. So minus 1 power n is minus 1. it follows that determinant of M is minus determinant of M. So, two determinant of M equals 0. But determinant of M is different from 0 in K by the non-degeneracy assumption. So the non-degeneracy assumption is exactly saying that the determinant is non-zero by the non-degeneracy assumption. And in fact, in my let me write it here. In the paper, I also wrote, and you also need that the home space between 1 and 1 is one dimension. But in fact, I don't remember why we use. I don't remember why I need to use that. So that's why I put it between parentheses. So this is assumed here. And I wrote that it is required here, but I don't remember why we did that. So maybe it is related to in the statement of proposition 4.1. Here you require, so it's a bilinear map. I see. So this is a bilinear map between that and that. And so this is a field. Okay, so where is it? So omega. So wait. So here omega. So here we don't need this to be a scalar. We don't consider, in fact, that it is a scalar. And I guess we assume in the proof of the corollary that we are getting a scalar. Yeah, it's a bilinear form. Yeah, bilinear. Yeah, okay, wow. Okay. Here, the notation is bilinear map. It's a bilinear map. It's not a bilinear form. Bilinear form means it maps to the scalar. But here, we don't assume this to be the scalar, so it's just a bilinear map. But here, it's a bilinear form. And in fact, the non-degeneracy of a bilinear, so the non-degeneracy of a bilinear, so you said that it's non-degenerate is equivalent to be a matrix like that. Non-zero determinant of the matrix, but this is for bilinear form, I guess. So bilinear form is represented by skew matrix. So maybe it's not a good way, not the good, that should not be written here, but maybe here. by the bilinear form. Satisfy. So let me write it here. Where the bilinear map is a bilinear form because on C1 equal the field. So I guess that's required here. Okay. So now I stated here that it is, so and one is the field, so I guess we don't need to add it here again. So in the paper it was written, but I will modify the paper. So anyway, just put into parentheses. I guess now we no more need to write it here. It is written here. It's enough. But I just keep it into parentheses. Okay. So this is non-zero. So we have this is 0, this is non-zero. So we must have this equal to 0. So thus 2 equals 0. Contradiction with the characteristic of the field different from 0, different from 2. So this is okay. So we get a contradiction. So the assumption was false, and the result followed. But let me restate what we prove here. This is something well known in algebra. In other words, a symplectic vector space over a field of characteristic different from 2 must be even dimensional. So this is well known, in fact, in algebra. In fact, I just reproved in few lines this well-known statement: a symplectic vector space over a field of characteristic non-2 must be even dimensional. So by reproving that, then I don't need to define what is a symplectic vector space. So this is just what we said. So let me just write the last line, and then we will make the pause. So the second from initial indicator of y star is 1. Is different from -1. So this is the hypothesis here was wrong. So it's different from -1. Then it must be equal to 1 by proposition 250. And we are done with this corollary. And we can make the pause. Okay, so that's okay. So we finished. Now we are ready to prove the theorem 1.1. So we are ready to prove Wang's conjecture in the hot case. So then we get expected proof of theorem 1.1, the Wang conjecture in the hot case. Proof of theorem 1.1. Okay, so the proof, in fact, will be very short. We've almost done everything. So by the natural adjunction isomorphism, which you can refer to previous semester or Techno book proposition 2.10.8. The dimension over the field of the home space y tensor 1 to 1 equal to the dimension of the home space of y between 1 morphism between y and y star. In fact, it is not just the dimension we are equal. By the natural adjunction of the morphism, these two home spaces are isomorphic. So in particular, the same dimension. But this is equal to 1 because y is isomorphic to y star is a simple object. Okay. And the field is algebraically closed, as I said. Then sure lemma, etc., etc. So, second equality, second isomorphism, dimension home space of X tensor, so X star tensor X, Y, equal to the dimension of similarly, it's not just the dimension which are equal, but the two home space are isomorphic by the natural adjunction isomorphism. So you move this here, you move this here, you multiply here, you should have X double star and here X star, so that's okay. But X double star is isomorphic to X. We are in a P, yeah. X double star is isomorphic to X because in a fusion category, because X double star isomorphic to X. Okay. Okay. So that's okay. Now, in fact, the what we get in the previous corollary, right here, you have this and this. But in the theorem, you here you have the other way. So it's okay. You know they are the same dimension. So if this one is odd, then this one is odd reciprocally. So it's okay. We don't have problem with that. Now we want to represent or to modelize this new bilinear form omega by the previous bilinear form we met in the preliminary section. Now, bilinear form we called B, and I hope, in fact, I read right. So lemma 3.2. Let me check something. 3.2. Fusion category, bilinear form. So I should write bilinear map here. If I want to be coherent with my notation, for 3.2, I should say bilinear map because I did not assume the and of one equal to the field. So I should fix that. Okay. So anyway, we only apply this for bilinear form, so it's okay here. So we apply, we consider the bilinear map here form in the preliminary section 3. So now, as I said, omega alpha beta is equal to B, composition of F and alpha beta, with B is the bilinear form from lemma 3.2. Remember, it was just a kind of straightforward bilinear form. You have something like that. That's all. This is a so the omega is really something trivial like that, but we need to to compose with something here. So you have the usual B, but we need to add something here. So this is nothing but that. So this is like the B, and you to compose with F. F is AX, tensor kappa, tensor identity. Star. And as I said, B is the bilinear map. Is the bilinear form here. From oh, okay, 3.2. But let me check again. So in 3.2, yeah, 3.2, we assume it to be a fusion category. We did. So, in fact, form and map was okay. We don't need to fix that. In the fusion category, we always have and of one equal to the field. So it's really a form. So there is no problem. No problem for 3.2. Sorry. So that's okay. Lemma 3.2, we assume the category to be fusion, and by definition of fusion, and of one is equal to the field. Okay, so let me come back to here. Okay. So as I said, we apply this, we use this bilinear form from lemma 3.2, but in lemma 3.2, you have only one string. But here we have three strings. So in fact, we need to take z from lemma 3.2 equal to this x tensor y tensor x star. So we have that. But so we automatically get the non-degeneracy because in the lemma 3.2, we already proved that this is non-degenerate. And F is an isomorphism. So this is non-degenerate. And we are done. So omega is non-degenerate. Degenerate by lemma. Remember the proof of lemma 3.2 and some previous preliminary result involve some technical result involving the basis. You have this basis, etc., with Kronecker delta. So the non-degeneracy was automatic. And the fact that F is an isomorphism. F is an isomorphism. So this pivotal structure is an isomorphism, identity is an isomorphism, and kappa. What is kappa? Kappa. So where is kappa? Kappa, kappa, kappa. Here. Kappa is the non-zero morphism between y and y star. Y equal y star. So it's a non-zero morphism. So it's a multiplic constant of the identity of y. So it's an isomorphism. Okay. So okay. So we, in fact, now, according to this dimension result and the non-degeneracy, we reduce to the corollary to 4.2. So the result follow by corollary 4.2. And we are done with this conjecture and with this section. So you see the proof was not so complicated as long as you write as long as you have the good preparation part. So you have a strong preparation part, a strong preliminary part, and then everything works quite easy. The tricky, in fact, the trickiest part was to think about such an argument involving symplectic vector space. Otherwise, everything is not so hard as long as you write the thing in the good order. You write the good the appropriate lemma and proposition. Okay. Okay. So that's why that was the first important, one of the main results of the paper, which is done. Now, we will we will more focus on the triangular prism equation. So as I said, the triangular prism equation is the consequence of of evaluating in two different ways the triangular prism using tetrahedron. So, but everything should be written in the context, the framework of monoidal category. So we need to define a monoidal tetrahedron, monoidal triangular prism. Of course, everything is labeled, and then we will be able to evaluate this monoidal triangular prism using this monoidal tetrahedra by two different ways and to get the triangular prism equation. But first we need, so the section 5 is the definition of monoidal tetrahedron. And some basic results involving symmetries. Because the tetrahedron is a very symmetrical graph. You have a lot of symmetry. Even if you write it in 3 dimensions, you have a lot of symmetry, more symmetry. Even in 2 dimensions, you have a lot of symmetry. But we cannot write it. It doesn't make sense to write this like that in a monoidal category. This should be every vertex should be a morphism, and you should be very careful how you write, how you modelize such tetrahedron to avoid any thing which will be non-well defined. Okay. So this section introduces the tetrahedron in a monoidal category. In monoidal category and prove some basic result corresponding to symmetries, more precisely to the cyclic permutation two, three, four. So this is a way to write a cyclic permutation, which generate the symmetric group. Generate the symmetric group F4 of the usual tetrahedron. More precisely, the orientation preserving symmetric group. We generate the orientation preserving symmetry group A4, so the alternative group A4 of the usual, of the regular, of the usual regular tetrahedron. Even I guess in 3D. Yeah. Symmetric group. So this section prove some basic result. Okay. So, I forgot what I wanted to say. I wanted to say something I forgot. Anyways. I forgot. So before defining the monoidal tetrahedron, we need and maybe we will have no time today, maybe tomorrow, because we need some technical lemma before. Yeah, I remember what I wanted to say. I wanted to say that the preliminary section 2 and 3 was not only dedicated to prove the Wang conjecture. In fact, we will also use them for to prove the triangular prism equation. So, okay. Definition. As I said, this definition will not be the definition of the monoidal tetrahedron. The definition of monoidal tetrahedron will be definition 5.4. We have one definition, one lemma, one remark, and then the definition of monoidal tetrahedron, which should be given tomorrow. So let's see. So let's see be a monoidal category with left dual. We will consider three functors between C cubed to the category of set, and we will consider natural transformation between these functors. And this natural transformation will be defined by picture. And in fact, this natural transformation will be very important during all the about triangular prism equation proof, because we will use, in fact, this notation almost everywhere. So this notation is quite important. Let's see be a monoidal category with left duals. Let F, G, H be functor from C cube to set define. So this functor will be defined as a composition of usual functor. So when you have a functor, when you state that something is a functor, in fact, it's not just I state something is is a function. So a function, okay, between a set and a set, you don't need to prove anything. But to state that something is a functor, you have to prove it is a functor. It's not automatic. And here, what I will define are really functor because they can be defined as a composition of usual functor. By usual functor, I mean functor you usually meet in category theory. So this functor from defined as the composition of usual functor such that f of x, y, z equals the home space between 1 and x tensor y tensor z. So you take 3 objects and you get a set here. It's a monoidal category. It is not assumed to be K-linear. So it's not a space here. It's a set. So this is the first functor. G of x, y, z is home C 1 y tensor z tensor x double star. Okay. H of x, y, z equal home space 1 between 1 home space, offset of morphism between 1 and x tensor y tensor z double star for all x, y, z in the category C. Okay, so we have, so as you see, this functor can be defined as the composition of usual functors. So you have the functor, for example, the home functor. If you take between 1t, map t to home between 1 and t. This is a functor. And you have the functor of x, y, z map to this tensor product, etc. Here you have the functor of double dual, etc. So everything can, this can be decomposed into usual functors. So there's no problem. Now, the natural transformation. So we will define a natural transformation between f and g and the one between g and f. Let rho between f and g and rho prime g and f be two natural transformation. Be natural transformations defined as follow by the following picture. So alpha is here a morphism in this set, and we will transform it into a morphism in his set. So you see here the difference. We will move something like that. So this is exactly the definition of this natural transformation. We are just moving like that. Here it's x, here it's y, here is z. So now you have here x double star. And rho prime of beta in this set will be just, in fact, the inverse, like that. Y, z, x double star, and x. Okay. So as I said, for all alpha in this Ohm's set, 1 x tensor y tensor z, and for all beta in this one, y tensor z tensor x double star. Okay. So we define two natural transformations like that. We will define two other, but that will require the existence of a pivotal structure, assuming the existence of a pivotal structure A, let two other natural transformation, sigma and sigma prime, so B natural transformation defined as follow. My following picture. Let me check something. Okay. So sigma of alpha is like that. So it's very easy. You just so yes, picture is bad. You just put a pivotal structure. AZ X, Y, Z. And the other way, you just put an inverse of pivotal structure. X, Y, Z. Double star. Et inverse. Here you have Z double star. Okay. So, prime. This is prime. Okay, so we define. And in fact, we will use everywhere in the rest of the course this natural transformation. So that will be very used. And again, for all. So the alpha is in the same home space as before, but gamma will be in the third one in the above list. So you will have gamma here. In home C, 1x plus y tensor Z double star. Okay. So this was a bit long for something very easy. And it remains 9 minutes. Okay. So I guess we will have time to at least to prove the first lemma about this natural transformation. I guess it will be enough for today. So following the previous definition, gamma, so sigma, so what is that? Rho and sigma are natural isomorphism. With rho inverse equal rho prime and sigma inverse equal sigma prime. Okay, so in fact, this is completely straightforward, in fact. So the proof only reduced to using zigzag relation. I guess, yeah. What I guess is that For people who are very comfortable with tensor category theory, such a lemma are not required. It's completely trivial. But that was not my case when I started to write this paper. I was not so comfortable. In fact, I started to write this paper before the 4th previous semester recovering the book about tensor category. And this is because of this 4th semester that I was able to write all the details in this book. Anyway, so how to prove that? So you compose rho and rho prime. So rho prime. You have a zigzag, so you just recover the alpha. So zigzag. So rho prime. You apply a zigzag relation. 2 times zigzag relation. You get directly that it is equal to alpha. So rho prime composed with rho is the identity of the functor f. Similarly, rho composed with rho prime is equal to the identity of the functor g. Okay. So they are inverse each other. Finally, for about the sigma and sigma prime, in fact, this is completely trivial because you just have you put pivotal structure and then you put the inverse. So you automatically get the identity in one way and the other way. We trivially have sigma prime composed with sigma equal identity of the functor f, and sigma composed with sigma prime equal identity of the functor h, which is what we wanted to prove in this lemma. Okay. That was straightforward. Okay. So I have time to write the next remark. In fact, by playing with alpha and rho, sigma and rho natural transformation, you can recover the map used in the definition of Frobenius indicator. If C is k-linear, pivotal, and x equal y equal z, then sigma inverse, so sigma prime, composed with rho of alpha. So I realize that the notation are not very nice because rho and sigma are natural transformation and alpha are morphism, but they are using the Greek letters. So it may be confusing, but yeah, alpha and rho are not of the same nature. So this composition is like that. So XXX. So rho and then sigma inverse. Which is, if you remember, exactly the map involved in the definition of Frobenius indicator. If, moreover, the home space is one-dimensional, as we already mentioned before, then remember that this reduced to identity times Frobenius indicator. So we have that equal to identity Frobenius indicator. So you can move this the other way. You get rho of alpha equals third Frobenius indicator of X sigma of alpha with sigma. So the third Frobenius indicator is a 3 root of unity, third root of unity by proposition 2.15. Okay. So you can go from if X equal Y equal Z, you can go from this natural transformation to this one up to a multiplicative constant equal to the third Frobenius indicator, which corresponds here when you are in some picture like that. We will see that later when we consider the tetrahedron and a triangular prism. You have a vertex which is labeled with some morphism. And what is this remark is saying is that if you want to move the label from one corner to another corner, you need to multiply by this multiplicative constant. Of course, you need this to be the same X. Okay, so that's this remark has a pictorial consequences. And that's all. In fact, tomorrow we will start with the definition of monoidal tetrahedron. End of session. So we can stop.